Okay. I think we can start. Uh, right. So, just a brief background about myself. I'm currently working as a research assistant at IIIT Delhi. And uh, by the way, this time last year, I was sitting on the opposite side of the screen and attending the suburban internship, just like you guys. And it's great to have the best guys in teaching us, and that's with my gratitude to them, and that's why I am able to present to you guys today. So if you guys have any questions, just feel free to interrupt me anytime. Right. So today we will be looking at the history of deep learning and understanding where PyTorch fits into the whole scenario. Guys, could someone confirm if am I audible clearly?
Yes, you are.
Okay, cool. The picture dates back to the year 2012, where actually we had the ImageNet competition, where the task was to have each of these images, and the aim was to classify which class out of 1,000 it belongs to. So, as you can see here, within our data set, we have pictures of dogs, cats, insects, birds, humans, flowers, vegetables, and a lot more. So, researchers were trying to build deep learning models back then that could efficiently classify uh, the image classroom, right? And in 2012, we had our first deep learning based architecture called AlexNet. So this AlexNet was actually the first
जरा
time
थोड़ा जोर से बोलिए
when
सर, सुनाई नहीं दे रहा है.
sorry,
हेलो सर.
We cannot hear your voice clearly.
just a second, guys. Hi guys, is it better now? Or can someone confirm? Really quickly,
Yes.
we are already running late. Okay, cool. The, I'll start my screen share again. Okay. Can you guys see my screen now?
Yes.
Yes,
Yes,
sir.
sir.
So I'll quickly start from the beginning. So it all started with the ImageNet competition back in 2012, where researchers were trying to classify which label the image belongs to. So there were 1,000 class labels to choose from dogs, insects, or vegetables, etc. And the AlexNet was the first deep learning based architecture that recorded around 15% error rate in 2012. And just to give you guys the difference of how better it performed, the second ranking in the leaderboard was a non-deep learning based framework, and that actually scored 26% error rate. So at that time, researchers realized what the two potential of deep learning models is. And this was the first model at that time that was coded on CUDA kernels. So CUDA is the programming interface that is given by NVIDIA that allows you to talk to your GPU and perform accelerated computing for your deep learning tasks. And back then, researchers were manually writing the code from hand. And many of you guys must have been familiar with the gradient descent algorithm, right? So in that, what you do is manually update the weights by doing back propagation and updating the weights after each epoch. So just to give you guys a context, this model had actually 60 million parameters in total, right? And 2 years down the line, there was another model that was trained by Google called InceptionNet. That was actually much better than the AlexNet, and it brought down the error rate down to single digits. I think it was somewhere around 7 to 8%. And uh, the number of parameters. Would anyone like to guess, like based on the image that you see in front of you, how many parameters this inception net would have? Like I told you, this model had roughly 60 million parameters. Like, would you just have a random guess on how many parameters this model contained? Anyone? Okay, I'll give you guys a hint. Or was it less than 60 million or greater than 60 million or roughly 60 million? Come on, guys. Let's make this a discussion, not a monologue. So I need your help here. Okay, someone typing in the chat. Let me see quickly. Okay, so okay, okay, so roughly 60 million, right? So that there's a surprise in here. This model actually contains roughly 5 to 10 million parameters. Like, would you you'll be amazed, right? We have lot more deep learning layers in our model, and whereas in the AlexNet we had pretty much less layers. So this was the beauty at that time that researchers were developing and giving that out to the open source community. And uh, a few years down the line, we have a ResNet model, and that employ the skip connections that we see in our transformers or the LLM models these days, right?
PyTorch इमेजेस में एनालिटिक्स करने के लिए यूज करते हैं.
Sorry, was there a question? Okay. Uh, so this is my implementation of a rather similar architecture based on the generative adversarial networks,
सर
where
क्या
using,
इसको काट रहे
sorry.
हैं? मेरे बाल वैसे ही नहीं है. हाँ, नीचे उतरा फ्लोर पे. इससे
But can we mute those who don't have a question?
नीचे थर्ड फ्लोर पे क्या हुआ भाई?
All right. So this is what I made a model from scratch based on the image-to-image translation, and this is based out of the generative adversarial networks. So here the task was to give our model, the generator, a noised image and a high-resolution image. So the model trains to filter out the noise, and we train a generator model that basically denoises your image and identifies the correct color scale. So we have in the middle row noised or blurred images, as one would say. And on the other hand, I have applied a color scale distortion. So as we can see, the actual image is on a different color rather than the or as compared to the noised image. So this is my implementation of a model from scratch that I implemented using PyTorch. So the researchers at that time were coding all these algorithms from scratch. So there was a need for a unified framework so that researchers would have an easy way to build more bigger and bigger models. So that is where we have PyTorch being used widely these days by the publication journals. Any new model that comes in is mostly PyTorch based. The Hugging Face repositories that you visit mostly contain code that is written in PyTorch. And the types of data that we have in our real world belongs to various modalities. We have image-based data, we have CT scans, we have table data, we have time series, and the most famous one is the textual data that we are interacting with these days using LLMs. Right. So the first step that model needs to know is you need to convert your data to standardized format. And for that, we have tensors in place. So a tensor is nothing but a generalized version of a matrix. So for building a tensor, we'll start from the most fundamental unit, which is a scalar number that is low dimensional, right? And if we have a collection of these scalar numbers along one dimension, we'll make a vector out of it. If we expand along columns, we'll make what we call a matrix of two dimensions. And if we generalize this concept to higher dimensions, we can have what we call a tensor in 3D or 4D or ND, right? And most of you might be using NumPy, right? So all of the functionalities within NumPy, like indexing, slicing, running basic linear algebra subroutines, or saving your tensor, or saving your NumPy arrays, or loading them back onto your notebooks, that might be already functional in NumPy, right? So all those objectives, PyTorch Tensor API takes care of, and there are many. So why was there a need to move on from Python to PyTorch for executing deep learning based models? Great. So the first point is actually that Python is a high level language as compared to C or C++, right? So the way a list is stored in Python is pretty different from what is required for deep learning models. So here we have an example of how Python list is stored in the memory. So each element in our list is actually given address in a separate space within our memory. And if we have a long list of these parameters, let's say 60 million, uh, calling a sparse memory view on that repeatedly over a number of iterations would be quite inefficient, right? Plus, storing these numbers is commonly done in floating point 32, right? So that would take a lot of space in Python. And as compared to C, the computations that we do, matrix multiplications or linear algebra routines, that are slow in Python. And on the other hand, we have a tensor that is stored in a memory. So uh, the way it is stored, we say it is continuous in memory. So by continuous, we mean the elements of tensor are stored one next to each other. So that way, I only allocate memory once to that tensor. And if I want to call a reshaped version of that, which I want to index, separate indices, slice a tensor, or do calculations on that, I'm using that tensor just once.
ছয় করতে বললে সে ছয় উল্টো পাল্টা করে দিচ্ছে তোর মা এটা ছয় খুলে দেয়
Guys, can you
একটু ভালো করে
can you mute if you don't have any questions? Okay. And that is where PyTorch comes in. So if we have 60 million parameters, so scaling a deep learning model in Python would be very slow. So this all functionality is offered by our PyTorch framework. Now we come on to our overview of what a deep learning project looks like. So as we saw, we have various modalities of data, right? We need to convert them to a standardized format that our model can understand. So we convert them to tensors, and with tensors, we associate for each number how the data type is stored in memory. So most commonly used data type is the floating point 32, and that is how we store tensors in memory. And after converting them to tensors, we'll collate them and make batches out of those. And then we start training our untrained model. So by untrained model, we have randomly initialized the weights and the bias using, let's say, ones or zeros or from normal distribution. So after running the training loop, we train our model for, let's say, 100 or 10,000 attacks. And at the end, what we'll be getting is something called a trained model. Now, during the training, we have various options like training our model on the CPU or a single GPU or multiple GPUs. And that basically allows you to train your model faster if your model contains a lot of parameters or your data set size is huge, as we saw in the case of the ImageNet competition. Right? And at the end, we have our trained model ready to be used. So we push it into production either to the cloud or our local server. And our today's code walkthrough will focus on how do we train the model and where does PyTorch help us to reduce our workload of computing the gradients, using optimizers, and doing all of the heavy lifting for us. So the first step after we have the tensors is to do a forward pass. So by forward pass, we propagate our input tensors through the model and calculate the outputs. And let's say we are performing classification, right? We have the ground truths with us. So let's say I classify four images wrongly. So I'll have some error quantified through that, right? So I'll be using that error value to back propagate my weights along my model, and at the end change the weights so that my error decreases. So this is the basic algorithm of gradient descent. And if we do this over multiple iterations, at the end we'll have a higher accuracy and our loss would be at the minimum, right? So that is our main objective of training a deep learning model. And on the parallel, so that we don't overfit, we keep separate examples so that the model doesn't see those during training. So we call this the validation data set. And along each epoch, when we are training our weights, what we'll do is evaluate on these unseen data points and calculate the loss function so that we don't run the risk of overfitting. Cool. Guys, do you have any questions until this moment? So we'll be moving on to the code after this. Let me know if you guys have any questions. Okay, cool.
Sir, what is the role of the batch tensor?
Sorry.
What is the role of the batch tensor?
Okay, so let me go back to the diagram quickly. Just a second. Right. So when we have converted each and every image into tensor representation, what we would like to do is we would, let's say you want to calculate a loss for each image at the end, right? You'll have, if we wrongly classified, let's say true image was of a dog and we mislabeled it as a cat, right? So I will have a some loss value associated with that misclassification, right? So along batch, if I have a batch to tensor, we'll have an average loss value that we'll be calculating for the set of the images that are within that batch. So we'll pass that whole batch tensor within our model at once. So that would be one step in our training epoch. Did that answer your question?
Yes, sir.
Okay, cool.
So what is batch size and epochs?
Okay, so our batch size is basically containing, let's say, within our training data set, we have, let's say, 1,000 images, right? And our batch size would be, let's say, you choose a batch size of 4 images. So at every forward propagation that you do for that model, you will be passing 4 images at a time through that model. So this batch size basically depends on your GPU RAM or a CPU RAM, that how many images at once you can load onto your RAM. So that will train your model faster if you can load a larger number of batches onto your RAM, right? And epochs is basically the number of iterations that we train our deep learning model for. So at the end of every epoch, I'll be passing that batch. Let's say we have a batch size of 4. So for our training data set, we'll have 250 batches, right? So after passing these 250 batches, that would make one epoch, right? And after the gradient descent updation, what I'll do is do this 250 batches for forward propagation again. So that would be the second iteration. And I do this for 10 times, let's say. So after 10 times, I'll have a trained model.
So, the performance of the model depends on epochs, right?
Right, right. Mhm.
Okay, thank you.
So you can actually visualize the loss function if you require more training epochs to get a more lower loss function. So you can obviously train it for longer iterations, not just 10. You can train it for 100 also. So that depends on your use case, right?
Sir, could you please tell about the epochs? Epochs is सर epochs में क्या होता है कि वो क्या सैंपल को तोड़ के रन करवाता है या फिर सब एक साथ रन होता है, इसमें होता क्या एक्चुअली में?
Right. So our batch size is basically we have 4 images that we pass at once. That is called the batch tensor that I explained right here. So this one would contain 4 images, and I have total 1,000 images, right? So if I do a simple division, I'll have 250 batches, right? That would be uh, forward propagated at one epoch. Right? So after that, I'll do this 250 batches again at the second iteration. So you pass these batches 250 times, and you do that for 10 iterations, right? So that would improve your loss. Did that answer your question? Or
Yes, sir. If you increase the number of epochs, then the result will be improved or not?
Yes, if your steps are all okay, your code is mathematically sound, and ideally, with on an average, your loss should decrease if you increase your iterations, right? So at the end of your let's say 10th iteration, let's say you get a loss value of 5, and you are not satisfied with that loss value. You want to see if we can reduce that. So you can obviously, instead of 10, you can increase that to 100 and see if your loss decreases to 2, let's say. So then you have a much better model, right? So that you can obviously play around with these parameters of batch size and epochs, and you can have a learning rate also. There's a parameter for learning rate that you can change so as to have a more control over your loss function. So ideally, it should decrease, and we'll see in the code also that how we can fall back to other safe mechanisms if the loss is not decreasing, right?
अगर सर मान लीजिए कि मेरा 96% एक्यूरेसी आता है पर एट द एंड 94 आ रहा है, तो उसमें जो मेरा फाइनल रिजल्ट होगा क्या होगा? 94 होगा, 96 होगा?
मैं आपका क्वेश्चन नहीं समझा, लाइक हाउ डिड यू गेट टू एक्यूरेसीज, कैन यू रिपीट?
नहीं सर, अगर लॉस फंक्शन में मान लीजिए अगर in the middle of the epochs, the loss function is like 10 and 0.10, and at the end there's a is so 0.20
Okay, so it increased, right?
at the end, yeah. तो सर
Okay,
हमें
so
कंसिडर कौन सा करना चाहिए?
right. So आप क्या करोगे? You'll check your parameters, right? Mostly the one parameter that would be responsible कि आपका पहले loss low आ रहा था and उसके बाद it increased, right? So the responsible parameter would be the learning rate. So let's say you have chosen a learning rate of let's say 1, and you said that earlier you were getting a loss value of 0.1, and at the end of 10 epochs you get 0.2. So it increased, right? So what you would do is you would decrease your learning rate so that your loss decreases. So that would be our first step to check. So ideally, the loss function would be the final, the loss value that you would consider is the final after the running of the whole for loop. So after 10 iterations, you will consider the last loss value.
Okay sir, I got it.
Do we have any more questions?
Yes,
Sir,
sir.
how is TensorFlow different from PyTorch?
Okay. So I'll give you just a couple of examples. So in TensorFlow, I don't know if you guys have used that dataset of BBC document classification or work with RNN models. Have you guys worked with it?
No, sir.
Okay. So basically, what we have is let's say we have a text uh, document. It contains 3 words, right? And there's another example, text2, which contains 4 words. So what we need to do is to pass this information to the model, we need to have a fixed length representation, right? After I convert this to tensor, let's say I have a tensor of length 3. For each word, I will have a index associated with it. Let's say the simplest label encoder, right? So for each word, you will map them onto their IDs, and you will have a tensor representation of that. Now, before you pass that onto the model, you need to have a fixed length vector, right, across your whole data set. You just can't pass 3 and 4 and expect the model to work. So that is one limitation of TensorFlow. So TensorFlow doesn't allow you to have this variability in tensor lengths when you train your model. So in other words, the way to put it is you have static computation graphs. So this part I was actually saving for the code walkthrough. So that would become more clearer when we understand what a computational graph is in PyTorch and how it is better than TensorFlow or other deep learning frameworks. And if we want to get another point of comparison between TensorFlow and PyTorch, so TensorFlow has a black box kind of structure, right? What you do is you make a model and then you compile your model with the optimizer, right? I think that's how you do. It's a long time since I used TensorFlow.
Yes,
So after you make your model, you do a compile and then you do fit, right? So most of these parameters, you don't have a direct access. So in other words, TensorFlow doesn't offer you that much flexibility as PyTorch does, as we'll see right now, how low level we can go. Like we can actually debug our code much better in PyTorch as compared to TensorFlow. So it doesn't give the user much freedom when you work with TensorFlow. And I already said there's another point of static versus dynamic graphs. So those are the most top 2 reasons for which I prefer PyTorch over TensorFlow. So I actually started with TensorFlow, and last year only I switched to PyTorch when I started learning deep learning.
Okay, sir.
Do we have any more questions?
Sir,
Okay,
how
so
NumPy arrays are different from tensors?
okay, that's a good question. That I actually skipped. Right. As I said, that basically PyTorch offers most of the functionality of NumPy arrays, right? And I explained that how NumPy array or a list is stored in Python, right? So the way you store the elements is separate in memory, so they are far away from each other, right? But in case of a tensor, you store the elements next to each other, very close to each other. So when, let's say, you have 60 million parameters for that AlexNet, right? And if you have 60 million parameters separated far away from each other in memory, and then what you will do during gradient descent is you'll update each of those 60 million parameters, right? At every pop. So calling them separately from memory is, let's say, very less sufficient when we have a lot of parameters in our model. So NumPy array was not the way the values were stored in NumPy array were just not suitable for our deep learning tasks. So that is how PyTorch fixes your memory issues that exist in NumPy array. Did that answer your question? Okay, guys, do we have any more questions?
Sir, can we run PyTorch on AMD GPUs?
Yes, I think you can. You can head over to the PyTorch official documentation. I'll let you know. So that was the next part in this session. So what you guys can do is, yeah. So you can head over to PyTorch, and you can actually study which GPUs it support. So maybe not the big older ones supported AMD, but maybe the current CUDA versions like the 11.8 or 12.1, they support the AMD GPUs. So you can appropriately figure out your dependencies, and you can choose the command and install for your system that fits best. So I'm not aware of what specification would run on AMD, but yeah, it is definitely out there.
Okay, thank you, sir.
Yeah, thank you. So do we have any more questions? So if not, we can move on to our code session. So you guys can see the notebook, right?
Yes, sir.
Okay, cool. So for our demo of so that we can understand the use of PyTorch better, we'll be having a look at a very simple model. So we'll be trying to fit a linear regression task using PyTorch. So guys, if you don't have any questions, can we move? Okay, cool. So we'll start with a very simple list of measurements. So on one hand, we have the temperature in Celsius scale, and on the other hand, we have the unknown scale temperature measurements. So what our task would be is to first convert this list of numbers to a tensor, and we can do that easily by calling toss.tensor on our list, and we can have a tensor storage for that. So our list converted from that Python memory to a tensor storage, as we saw earlier. So now we are ready to use these tensors for our model. And for any deep learning project or any machine learning project for that case, what I would prefer you guys to do is to go out there and just before starting anything, writing a model, loss function, gradient descent, you guys just do a visualization for your data. That would give you a much more better idea of what your model is expected to do, or what would be a better model assumption, so that you could explain your data and generalize on future test cases well, right? So what we'll do is we'll plot the Celsius on y-axis and our unknown scale on the x-axis. And as you guys can see, you guys might have predicted our linear model would fit the best, right? That is the question. Okay. Guys, can you mute if you don't ask any questions? That would be helpful. Okay. So what we will start with is a very simple functional form assumption for our model, which would be a linear model, right? So what we'll do is we have the unknown scale temperature measurements, and our model would be very simple. We'll multiply a weight term with it and have a additive scalar, which we'll call the bias term, right? This would be our simple model that we guessed could fit our data based on the scatter chart, right? So we have this formula, and now we'll put this into a Python function, which would take in the arguments of unknown measurements, our weights and bias, and we'll be returning our temperature predicted, right? And after that, to see how far my predicted temperature is, how far it is away from our actual Celsius measurements, we'll use a mean squared loss function. I guess that's most widely used loss type of loss function for regression-based tasks. So we'll be keeping it simple, and basically it looks like we take the difference with our actual Celsius measurements and take the square. And after that, we sum it over all of our training examples. So here we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 training examples. So for individual predictions, we'll take the difference, we'll square it, and then take the average over the 11 examples. So this is how we would get a single loss value at the end. So we'll put this equation into a Python function again and define a loss function for it, which would return our mean squared loss error, right? So a best way to build, start creating any model is to just randomly initialize the parameters. So as I explained earlier, our model just has one weight and one bias, right? So we'll randomly select, let's say I'll pick 1 for weight and 0 for bias. And PyTorch allows us to easily instantiate these parameters. So by calling torch.once with empty brackets. So by empty brackets, I mean I want a scalar at the end. I don't want a shaped tensor, like let's say a 1 cross 1, right? I just want a single scalar. So by passing in empty brackets, I'll have weights equal to 1 and bias equal to 0. And just to see if our functions work well, we'll pass in these parameters through our model function that we defined above, and we check how the prediction tensors looks like. So here we have for each of the 11 unknown scale measurements, we initialize the weights and the bias, and based on that, we are having individual predictions for that. Now, this is the aim that we need to.
ज़्यादा difference तो नहीं आया.
May I ask a
that
question?
मैं तो अपने देख के
Hello?
बता रहा हूँ ना. अगर उसके मेरे में difference आया.
I want to ask a question.
Sure, go ahead.
What does these methods functions return ones and zeros, and what is actually do?
Yeah, so torch.ones actually allows you to create a tensor that contains ones, right? So using torch.ones, this method allows me to basically start a tensor that just has ones in it, right? And with torch.zeros, I'll have a tensor that just contains zeros. So after that, within that ones function, the argument that we pass in is a shape, right? So the shape is equal to an empty bracket, right? So by empty bracket, I just want a scalar. If I don't pass in any shape within that, let's say 1 cross 1, uh, I have this kernel restarted. Let me just run it again so I can show you how it looks like, right? So this was our original code, right? Let's change this and compare with our new one. So the first parameter is the shape that we pass. Let's say I pass in 1, 1 and print out what the W looks like. So we'll now have a tensor of shape 1, 1 instead of a scalar, right? So if I, let's say, pass in 3, 1, I'll have a vector of length 1, right? Or vector of length 3 that just contains ones, right? So PyTorch easily allows you to start off with random weights or bias by constructing a vector that just contains ones or zeros. Did that answer your question?
Yeah, thank you.
Okay. You can interrupt me at any time if you have any questions. So moving on, uh, we check. We already checked that our prediction is working well. That the model that we defined above is working well. We are having a tensor of length 11 for each unknown measurement. We are having a prediction, right? And after that, we'll calculate the loss and we check uh, that it is a scalar tensor, right? So it's just a single loss value for each of these 11 predictions combined. Now, the next task in a machine learning environment is to update your weights and bias so that the loss decreases. So a way to do that is to reduce your parameters in that direction in which the loss is minimized. So the direction is actually given by the gradient vector. And the way we calculate gradient is we take the derivative of our loss function with respect to the basically the model parameters. So alpha I here represents weights or bias. So if we take the derivative and we apply the chain rule, the first term will be the derivative of loss with respect to our model predictions, which is the TP, which is the function that we defined here, right? And the next term in the chain rule will be to take the derivative of the model with respect to the model parameters actually. So this way you can have a gradient vector for each of your weights or bias within your model. Now to calculate this derivative, I hope you guys are familiar with calculus. So what I do is we take the derivative of this loss term with respect to TP. So when I take that derivative, the 2 will come forward and the rest of the expression would remain same, right? So this is how the actual derivative would look like. We convert this formula again into a loss function. Python function that computes the derivative of the loss function. So the whole game is to write your maths and put it into functions. So that way, at each step, you know you are right. And you can evaluate by passing in dummy variables and checking that your model is working fine. And after that, what we do is we are left with the second term, right? The derivative of the model with respect to the actual parameters. So when we do that, we have the derivative of TP. So when I go back to my TP is the model that we actually assume. So the functional form was basically weight times R TU plus B. So when I take the derivative of this with respect to W, the first term will give me TU and the next term will be 0. And when I compute it for bias, the first term will be 0 and the next term will be 1. So this is what these two formulas mean. And when I put these two within my function called the derivative of the model with respect to weights and the derivative of the model with respect to bias, I'll be then ready to calculate or formulate a function that gives me gradient at once. So these individual functions that we calculated, that we defined in Python, will be putting them all under one function, and that would return us the gradient vector. So each term in that vector is belonging to the gradient of the loss function with respect to that parameter, right? So the first term would be the derivative with respect to weights, and the next term is the derivative with respect to the bias, right? And as we saw the formula for gradient above, we'll be substituting that here, and we already made functions for that, right? So we'll compute a gradient vector at the end by stacking. So after multiplication of these two parameters, right? These two by the chain rule that we got. So what we'll do is stack these parameters one on top of, or stack these individual gradients one on top of the other. So PyTorch allows you to do this by using torch.stack. And what you can do is pass your individual elements within a list. So the first term was the D loss with respect to DW, right? So this was the above element. And the next element was loss with respect to the bias. So what we do is we'll have that for our each of the 11 measurements. So what we'll do is we'll take a sum of that to get a single value for that across our 11 examples, right? And to check that our gradient is functioning well, we'll print out the gradient vector and we get a gradient with respect to weight and a gradient with respect to bias. So till this moment, we are good to go and we don't have any issues, right? So the next task and the final before we start our training is to update your weights. Alpha is the weight, so weight or alpha is the parameters, the model parameters. So it can be weight, your bias, or just not just two. You can have a million parameters. Using this single equation, we can update all of this. So what we do is we have a gradient direction that would specify in which direction to update my parameters in. But the direction is not just a single quantity that we need to take into account. We need to have a step size for that as well, like how much down I need to go in the direction of gradient to update my alpha parameters, right? So that is quantified by our learning rate. So we have a learning rate that quantifies the step size. We have a direction. So we go that many units in the gradient's direction and update my alpha parameters after every epoch. So this is the basic algorithm of our gradient descent, and we put this into a training loop. Now, this training loop, you can consider it as a boilerplate code. So boilerplate code is nothing but just a simple code that you can run anywhere, and the representation or the logic would remain true for this model or the LXNet or any number of, let's say you're training a LLM as well. So there also the training loop structure remains the same. So what we do is we pass in our number of epochs, that how many iterations for we'll be training our model for actually. And the next is the learning rate that defines our step sizes. We have our model parameters and we have our x and y values. So what we do is we'll come back to this print parameters equal to false argument later. But let's start with our for loop. So our for loop starts with we have a tensor of this parameter. So our parameters would look something like this, right? Torch dot tensor of 1 comma 0. So the first one is the weight and the next one is the bias. So this is a way we can include weight and bias within a single tensor, right? As we saw earlier. So we were randomly initializing our weight to be one scalar, and bias was zero scalar, right? So we can put them under one single tensor by using torch.tensor like this. And what we do in the first step is unpack this. So the first element would be the weight, and the next one would be bias. So this is what we are doing in the first step. Then using the weights and bias, we call the model and do a forward propagation. So after the forward pass, we'll have our predictions, TP. Now to quantify how far these TPs are from our actual T cell shapes, we'll use a loss function and come up with a loss value, right? Now this loss will be used to calculate the gradient, and we'll be using our gradient function that we defined above to calculate the gradient vector. So we'll get something like this at the end of this gradient step. Now we need to update our parameters, right? So after calculating the gradient, what we do is put this formula as it is into our code logic. And this way, after every epoch, my parameters will be updated according to the gradient vector. Now, this is where I think PyTorch is better than TensorFlow. So what you do is you have instead of running model.fit in TensorFlow and just seeing just seeing the training loss and not the actual gradients, what you can do here in Torch is you can define a parameter called the print params equal to false. So if you set this to actually true, so I have by default set it to false, but if you set it to true and run this, what will happen is you'll get the actual numbers that are contained within the parameters and gradients after every epoch. So along with visualizing what the loss is using this print statement, you can also check what the actual weights and the bias look like along with the gradients. So let's say if you have chosen a wrong learning rate, so your gradients would explode, right? So to make sure that doesn't happen, you can use print statements within your training group to be safe from overshooting or over exploding gradients, right? And below is an example of exactly that what I talked about. So what we do is do a dry run for 100 epochs. So I'm training my linear model that we defined above for 100 iterations, and we are setting the learning rate equal to 0.01. Guys, is there a question? Okay. So what we defined above is a weight and a bias equal to 1 and 0 respectively, right? We put that into a tensor that we unpack at the starting of our epochs for loop, right? Weight and the bias. And the next is our unknown scale measurements and the Celsius scale measurements. We'll set here print params equal to true. And what we see here is basically loss is increasing as one of you asked initially in this talk, right? So what our loss is doing is actually as our epochs pass by, our loss is actually increasing, right? And you guys can see here that our parameters is also the magnitude of the parameters is also shooting up, and our gradients are also very high. So any guesses as to where we might be going wrong? What parameter should we fix in order to reduce our loss function?
Sir, we can reduce our learning rate.
Yes, exactly. So what we'll be doing, we'll be reducing our learning rate down to 0.001. So we'll be having a much more lower learning rate. As we can see, we are going from 17,000 to 300 and then 78 and so on, right? And at the end of 100th iteration, we are getting 29.023 as the final loss value. And these are the updated parameters, the final weights and bias that we have updated from starting from 1, 0, right? So these are the final parameters after 100 iterations. I hope up till here we are all good. So the next problem, if you guys see that in the very first epoch, this is where we added those print statements. Those will come in handy. So the first epoch, we were getting a gradient for the vector term, for the weight term, which was actually 5 times that of bias, right? And if we have a fixed learning rate for both weight and bias, that wouldn't be a meaningful update, right? So let's say I take 0.001 as my learning rate, right? The gradient vector will be multiplied with this, right? As we saw above. So it will be zero point 0.4 of a delta step for the weight term, right? But for the bias, it will be 0.008, which is much small as compared to zero point 0.4, right? So these updates for weights and bias are not running on a equal scale. So what we need to do is normalize our inputs. So as we saw earlier, that are unknown scale measurements, I have also printed those here that are minimum and maximum. It is ranging from 20 to 80. So what we need to do is we can have a min-max normalization or mean standard deviation normalization, but a very crude way to normalize it is to divide the measurements by 10. So what we'll have is the range of the unknown scale measurements going from 2 to 8. So now we have a much more compact range, and we'll see how this helps us to improve our gradients, right? And what we changed is, again, uh, by normalization, we have allowed our learning rate to increase so that we can train our model faster, right? Our loss would decrease to zero much more quickly, as if when we were using a learning rate of 1 e to the power minus 4, right? So by normalization, I can use a higher learning rate and I would go to the loss quickly, decrease my loss quickly. So initially we saw, right, our gradients, the gradient term for the weight was actually 50 times that of the bias, but now it's just 7 times, right? It's much more on a relative scale. We have a same range for the weights and bias. So what we have at the end of 100 epochs is a very lower loss, right, than 29, that what we were getting earlier, right? So now we are good to train this model for, let's say, 10,000 epochs. And when we do that, our loss actually goes down to much lower value, 2.928. And what we have is this final weight and the bias parameters, which are finally updated using gradient descent of 10,000 epochs. Now, our this was what we predicted, right, with the weight and the bias. So what we are doing here is we actually multiplied our values with zero point 0.1, right? So what we are doing here is we are multiplying this weight term also with zero point 0.1, and we are showing it here. And then is the bias term, right? And if we see the actual relationship between the Celsius and the unknown scale was close to something like this. Sorry, right. So any ideas what this unknown scale is in the real world? What this relationship looks like to you? What is the other temperature scale that we just modeled right now?
Sir, can you
Okay.
explain TU and TC in detail?
So okay. So TC is
Sir, I think
basically
you have
our
weight and bias.
okay. No. So TC is our temperature in Celsius scale, and TU is the unknown scale temperature measurement, right? And what we were doing is TP was the prediction by the model, right? And the prediction is what we were comparing with the Celsius scale. I hope that's clear, right? Okay. I'll take that as a yes, and all right. So this is the actual relationship that are this is the model parameters. Okay, this is the relationship according to the model parameters, the first one, and the next one is the actual one. So what we just modeled is the relationship between Fahrenheit and the Celsius scale, and right, we are getting pretty close numbers to the actual values, right? So what we just did is using a linear model and a mean squared loss function, we updated our parameters using gradient descent and predicted a relationship between the Fahrenheit and the Celsius scale temperature using the uh, PyTorch tensor. So in our model, we just have two parameters, right? The weight and the bias. But let's say we were doing this for the Alex set or a very bigger model, let's say LLM, where we have billions of parameters. So writing the gradient function by hand and calculating the update step uh, for 60 million parameters would be quite huge, right? You would not be able to track their differentiation parameters and make a very complex solution, right? That would just not be feasible. So this is just a relationship that we plotted on the XY axis. This is just a good way to check that how your line fits the actual data. This is just a sanity check that we do. But where PyTorch comes in is they make use of an engine called autograd. So that does the differentiation for you automatically. You don't have to do the gradient function, the update to find the parameters. That will be done by PyTorch for you. So what we change in our code is initially we were just uh, initializing our weights and bias, which are the model parameters, just up till this moment, right? But what we do is we specify the data type of it to be torch.float. So instead of telling PyTorch to recognize it as integers, I'm saying you consider them as float. And I add a very crucial parameter next to it, which says requires grad equal to true. So this allows PyTorch to track the gradient vectors for the parameters automatically without me having to calculate for, let's say, 60 million parameters. So this way I can leverage PyTorch to automatically do differentiation for me. So what we do to understand this better, what we do is do a forward pass, right? So I have the normalized scale measurements that we multiplied with 0.1, right? And we unpack the parameters. So the first one was weight and the next one was bias. I predict the temperature. The predicted temperatures, I'll compare them against the Celsius scale measurements and calculate the loss. Now, after that, what we did is calculate the gradient. But we made a gradient function for that, right? And for that, we had to calculate the differentials by hand. So instead of that, if I just do loss dot backward, PyTorch will automatically calculate the gradients for me. So here, as you can see, when I specified requires grad equal to true, and I print the gradient parameter for these parameters, right? I get none because there were none. We didn't do any gradient update step. But after we do loss dot backward, and then we print the gradients for these parameters, we get some finite numbers, right? Using loss dot backward. So this is where most of the heavy lifting by PyTorch is done for you. So to understand this better, we have a computational graph. So what we did is our x is the temperature that we had in our starting code block, right? So this is that unknown scale measurement, right? And that we were multiplying with a weight, and we were adding a bias term next to it. So the arrows here signify how the information flows through the graph, right? So after I multiply x with w, I'll add bias to it. And after I get the model predictions at this arrow, what I do is calculate the difference between the Celsius and the model predictions. And after that, what I did is do the square of it. And that's how I calculate the loss. So this is how a computational graph would look like if you could visualize what happens under the hood in PyTorch. And what PyTorch did is when I said requires grad equal to true, and when I did loss dot backward, what it did is something amazing. So for you guys, it automatically performed the gradient back propagation. So the yellow arrows actually specify the backward pass. So when I did loss dot backward, so I'm going backward at every step in my computational graph. So I go backward until and unless I reach the weights and bias. So for them, I had specified requires grad equal to true, right? So for them, our gradients will be stored. And when I store them, I'll automatically have the gradient calculations without me having to do it manually. So this is where most of the computations happen in PyTorch for you. So this is the autograd engine that works behind the scenes to calculate the gradients for you. So let's say you have 60 million parameters instead of two. You'll just do loss dot backward, and you'll have gradients for all of the 60 million parameters calculated just in one step. Are we good until here? Or do we have any doubts? I know this is this is the only step that needs attention to detail, but I I assure you this is the only thing that you need to know for building more bigger deep learning models, right? Let me know if you guys have any questions. So the other thing was we updated our parameters, right? At that step, let's go to our original training loop, right? This gradient function that we specified, instead of that, we did lost on backward, right? And the next thing was to update the two parameters here. But instead of two, there could be a lot more parameters, right? So this also PyTorch does it for you easily. What you need to do is just use their Optim library within Torch, and within that, what you have is various optimizers like stochastic gradient descent. We have autograd, we have RMS prop, we have various optimizers that do the update step for you without you having to actually do it, right? So what we did is we have the parameters instantiated like the way we did above with the requires grad equal to 2. So this allows PyTorch to track the gradients for these parameters, right? And what we do is we specify the learning rate. So that learning rate will be passed into an argument for that optimizer. And along with that, optimizer stores a reference to the model parameters that we pass within a list, right? The parameters that we instantiate will be passed to a list, and that will be given as an argument to our optimizer. So after we create optimizer, we do the previous two steps. We calculate the predictions, we calculate the loss, we do loss dot backward, we print the parameters. But after, so just to stop here, when we do loss dot backward, we just calculated the gradients. We didn't update that parameters using those gradients. So I have printed here, the parameters are still 1 and 0. The weight is 1 and the bias is 0. But when I do optimizer dot step, what I have is the gradient times learning rate. That subtraction is being done for me here. So the parameters now have changed after I do optimizer dot step. So are we guys good to go until this point, right? Do we have any questions? Okay, cool. So the last thing you just need to know is how this is being performed under the hood. I know for some of you this might not be that meaningful, but for those who want to go into research and understand what happens behind the scenes, this is very meaningful. This would be meaningful for you guys to understand. So what happens is when I did the above steps, I stored the parameters within the model. And here we have the loss function as part of the computational graph. And when I did optimizer here, this step, this step actually stored a reference of those parameters, right? We actually passed those parameters within the list of the optimizer. So what optimizer did was store a reference to those parameters. Now, when I did the forward pass, TP, and calculate the loss, I reach at the B image, right? I give an input, I have an output, I compare those output with the actual outputs of the Celsius scale measurements and calculate the loss. Now, when I do loss dot backward, what I do is accumulate those gradients for those parameters, right? And when I update the model parameters gradients, what we did initially was optimizer was storing the reference to those parameters, right? So those parameters got a gradient update within the optimizer also. And when I did optimizer dot step, we reach to the last D stage. So it does that update step for you when you do call optimizer dot step. So this is the entire functioning of the code blocks that we executed above. So the loss dot backward and the optimizer dot step is being taken care of. What's the question? Okay. Cool. So here we have our final training loop. So with the changes that we made earlier, right? Instead of having the gradient function that we wrote earlier, we will be doing lost on backward. And instead of updating the parameters manually, we'll be using optimizer dot step to do that for us. And optimizer dot zero grad, what that does for you is, let's say, at the end of the first iteration, you'll be having these gradients stored within your computational graph, right? But at the start of the next iteration, you want new gradients to be stored here, right? So what you do is you do a flushing of these gradients. So by calling optimizer dot zero grad, I remove the gradients from the previous iteration because I don't want them to contaminate my gradients that will be coming from the second epoch, right? So that is how we remove the gradients from the previous iteration by calling optimizer.zeroGrad. And the rest of the function remains the same. And we return our model parameters at the end of the training iteration. Now we compare this with our handwritten gradient functions and optimizer step just to run it for 10,000 iterations with a learning rate of 10 to the power minus 2. We input the normalized that we multiplied with 0.1 and calculate the loss at the end of 10,000 iterations. We get exactly the same the way we were getting before, right? So this actually verifies your proof of concept or your math that you applied to code, that you're getting exactly the same result with PyTorch doing the gradient calculations for you automatically. So let me know if you have any questions up until this moment. I know this was not to digest. So please feel free to ask some questions now. Anyone?
Sir, could you please just scroll up
Mhm.
this training loop for PyTorch? Niche.
Okay, this one. Right?
Yes, this one.
Mhm.
Sir, in this optimizer.zeroGrad, what's it doing?
Right.
Could you
So
please
let's say
explain it again?
yeah. So let's say this step I didn't include. Let's do dry run of two epochs manually, right? Let's say we are at the first epoch. So what I would do is calculate the TP. Based on the TP, I'll calculate the loss rate. And because we don't have this step, I commented it out. Let's go to the lost or backward. We calculate the gradients at this step, right? And what I do at optimizer.step is update the parameters using those gradients. Let's ignore the print statements also, right? Just focus on these four code lines. And this is the end of our first epoch, right? Did you understand up
Right.
until this moment?
Right.
Right. So what we did is when I did lost or backward, let's come to this diagram again. When I did lost or backward, PyTorch within the computational graph, it stored for me these gradient values, right? With the weight and the bias. What is the gradient of that, right? PyTorch stored it for me. But when I come to the second epoch, I will have fresh gradients, right? I'll calculate the gradients again. But when let's say I didn't do this zero grad thing, and when I come to the next epoch, second epoch, I'll do the predictions again, calculate the predictions again, calculate the loss again, and what I'll do is loss dot backward without doing this optimizer dot zero grad. So what loss dot backward will do is we'll have the gradients from first epoch and the newly calculated gradients in the second epoch will be added to them. But that's not what we wrote in math, right? Because each epoch is independent, right? I'll have new gradients calculated. So what I do is I need to remove these gradients from the previous iterations. So what I do is call optimizer.zeroGrad to zero out the gradients from the previous iterations.
Okay.
Do you guys have any more questions? Just let me know. This was the total code walkthrough. This is the end of my talk. Just let me know where I missed you guys or just skipped any code logic, skip to explain you guys what that code line means. Just let me know.
This notebook will be shared, right?
Yeah, so I'll provide that to the Subudh officials and they can pass it on to you guys. But if you guys are curious, I have already hosted this along with my notes on GitHub. So where you can find it on my public GitHub repo. So I have already shared it here. So these notebooks and these notes are already available. So I'll share this link with you guys in the chat and you guys can also play along with it. Guys, any more questions from the
Sir,
code or the previous notes? Yeah.
sir, I want to ask a general question, sir. In your opinion, what should a beginner focus on? Like, he should focus on math or code if he wants to learn deep learning?
Right. So here, as you can see, they both go hand in hand, right? You can't just single out maths and single out code, right? You write your uh, formulas and then you implement it in code. So I think the best way to do is do them both together, just by building smaller models like this. You can do a dry run for this in case of a logistic regression dataset, right? And you can practice out this notebook for that use case. And I guess that would be a way to exercise your both math and coding skills. So this is not just limited to PyTorch. This applies to any other field that you guys might be working in.
Okay, sir.
Any concept that you guys want to revisit again? Okay. I think we have overshoot by quite some time. Let me know if you have any questions from the